Hi, and welcome to Failurology, a podcast about engineering failures. I'm your host, Nicole.
And I'm Brian, and we're both from Calgary, Alberta, Canada.
Thank you again to our Patreon subscribers.
For less than the cost of a decent beer up here in Canada, you can hear us talk about more interesting engineering failures.
Actually, it's probably like half the cost of a beer.
I mean, it depends how you define decent beer.
Fair enough. Beer's expensive. Good beer's expensive.
This is true. Especially for our American listeners, alcohol up here in Canada is substantially more expensive than what it is in the States.
Yes, it is.
However, we seem to drink an excessive amount of it compared to the States as well.
There's not as much to do up here. We gotta keep ourselves occupied.
Canada's pretty much like Wisconsin level of drinking.
It's one of our special skills.
And playing hockey.
Beer and hockey, yeah, I was just gonna say that. This week in engineering news, underwater adhesives. Marine organisms such as mussels secrete adhesive proteins, allowing them to stick to things underwater.
That's really cool.
For us humans, though, it's hard enough to find adhesives that work when wet, let alone underwater. I don't know if you've ever tried to use duct tape when wet. It does not work.
Or cold. Duct tape does not work well in the cold.
Oh, that's good to know. Duct tape is not very good tape. It's very versatile, but it's not very, very good adhesive. Anyways, McKelvey School of Engineering at Washington University in St. Louis developed a research project to come up with adhesives that would work underwater. They engineered microbes which produce the necessary ingredients for biocompatible adhesive hydrogel that's stronger than spider silk and as adhesive as the mussel foot protein.
Two things that we all want in adhesives.
You will. I know you made that as a joke, but you will when you hear the rest of this. They experimented with mussel foot protein adhesives before, but those adhesives quickly diffused underwater and were therefore very hard to use. Even when they could get it to work, the adhesive would stick to the two surfaces, but then not to itself.
Kind of like separating an Oreo cookie and getting cream filling on both sides.
The trick was the spider silk. When they mixed it with the mussel foot protein, they synthesized a trihybrid protein that was as strong as spider silk and as adhesive as the mussel foot protein. It's also biocompatible and biodegradable. The hydrogel is slightly more dense than water, so it is easy to work with, which is definitely a bonus. And the main application that they're hoping to use this underwater adhesive for is tissue repair, specifically for rotator cuff surgeries, but I think there are a lot of applications for this type of product. I also want to mention that the mussel that I'm referring to is the shellfish animal, not the muscles in your body. So mussel, in case that didn't make sense.
Spelled differently, and I assume they taste different as well.
That's disgusting.
But this is probably one of the coolest engineering news segments that we've ever covered.
Really?
I think it's the coolest one that we've done.
It's really cool. I mean, we've done some really cool ones, but yeah, this one's really interesting. Yeah, I mean, when have you ever glued something underwater? The answer is never. Until now, which is pretty cool. If you want to read more on this study, check out the link on the webpage for this episode at failurology.ca.
The new season of the 32-team Professional Hockey League that plays in Canada and the United States has started, which means the Toronto Professional Hockey Team might win the end-of-season mug.
When hell finally freezes over and the Toronto Professional Hockey Team wins the big game, there's definitely going to be a parade.
Toronto Professional Hockey Team Parade Planning Services is your one-stop sports mug championship parade planning service.
Don't be like Vancouver. They rioted because their professional hockey team has never won a championship.
Call Toronto Professional Hockey Team Parade Planning Services toll-free at 1-866-865-1967.
Now, on to this week's marvelous engineering episode. Coincidentally, an engineering marvel that we do every 10 episodes. On this week's episode, we're going to cover the CN Tower, which is located in Toronto, Ontario, Canada.
I just want to say, I know we did our 1-year anniversary episode. You know, that was episode 36, so that wasn't that long ago. But we have 40 episodes, 40. That's huge. That's so cool. Yay, team. And thank you to all of our listeners for listening to our episodes, downloading them, supporting our show, reaching out to us and talking about all these failures, nerding out about them, sending us failures to talk about. Greatly appreciated. We love it.
Yeah, without you, it's just Nicole and I talking about an engineering failure, and nobody gets to hear us talk about it except us.
I mean, we'd probably still talk about it because these are really interesting. But it's really nice to know that people are listening and enjoying. I've said before, I'm reading about this anyways. Now I'm just writing it down and recording it. This stuff is so interesting.
The CN Tower is located at 290 Brenner Boulevard in downtown Toronto, and it was built on former railway lines, hence the name for CN, or Canadian National, the company railway line that built the tower, although it's now owned by Canada Lands Company. The CN Tower is the world's 9th tallest freestanding structure, was the tallest until 2007 when it was surpassed by the Burj Khalifa. It is still the tallest freestanding structure in the Western Hemisphere, though. So it's got that going for it.
That's pretty cool. I knew that it was up there, but I didn't realize that it still held that title of tallest freestanding structure in the Western Hemisphere. Yeah, I thought there were other towers that had surpassed it by now. Because this tower was built in the 70s, so you'd think someone would have built a taller one by now.
Yeah, it is a really, really tall tower. It's in downtown Toronto. I think what helps it to be part of the tallest tower is that 90% of it is just basically a core for the elevators, and there's no usable real estate for a significant portion of it. So there's an observation deck and some other stuff on the top, but the bulk of the tower is basically just a big concrete shell or shaft to give it some height. So it's not as functional as the Burj Khalifa.
True, good point.
It did win one of the American Society Civil Engineers 7 Wonders of the Modern World awards, which is, again, another thing it's got going for it.
Also, fun fact, and if you may or may not have picked up on this, but the first Marvel episode we did on the International Space Station, but since then we've kind of just been picking off the 7 Wonders of the Modern World. We're just kind of working through that list, and they're all really cool. Like a lot of these, I go into them thinking, oh yeah, sure, it's a tower, cool. So interesting how they built it and the different engineering feats that they had to overcome and the different tools and techniques that they used. Some of them were really, really, complex and new tech, and some of them were really basic and, things that they've been doing for decades, but they just worked so well that they decided to use them here. So definitely really, really interesting.
Yeah, so the CN Tower, it's 457 meters to the roof, 553 meters to the antenna array on the top, which is equivalent to a 147-story building. That's really, really, really tall.
For reference, the Calgary Tower is 191 meters to the top of the spire. It's just a little baby tower. We have office buildings around it that are taller than it, but we love it nonetheless.
Construction of the tower started in 1973, it was finished in 1976, and the tower opened to the public on June the 26th, 1976. It cost 63 million Canadian dollars to build it back in the day. To build a tower that tall, that seems fairly cheap, even with what we have for inflation. Like, this is a significant structure. It's still in the top 10 freestanding structures in the world. So it's classified as mixed use. It has observation, telecommunications, it's an attraction, there's a restaurant in it, and it attracts more than 2 million international visitors annually. I had the opportunity this summer a couple times to go to Toronto Blue Jays baseball games, and the CN Tower is right beside Rogers Centre where the Blue Jays play. So it's a very cool structure just to see right kind of by the harbor in downtown in Toronto. I highly recommend at least looking at it if you go to Toronto.
The original plan for the tower was a tripod with 3 independent cylindrical pillars linked at various heights by structural bridges. This would have resulted in a shorter tower, and over time the vision evolved to the one that we see today, which is a hollow concrete hexagonal pillar containing stairwells, power, and plumbing connections. There are 6 elevators in the tower, 2 each on 3 of the 6 sides. And the elevators, cabs, and shafts are lined with glass. The skypod, which was originally called the space deck, was not part of the original concept, but it was added during construction because one engineer thought that visitors might pay extra for a higher observation deck. So the CN Tower has 2 observation decks, one lower that you get standard, and then the skypod, the upper one that you pay extra for.
Yeah, and I believe recently they added the edge walking experience, so you can actually go outside of the CN Tower, you're in a harness and attached to, I assume it's some sort of cable system where you can actually walk around the edge of the CN Tower at 356 meters above the ground. So 116 stories above the ground, you can go for a walk outside.
No, thank you. And that just reminded me that when I was researching this the entire time, my hands were sweaty. And do you want to know why I remember that? Because they just did it again. I'm not a heights person, and it makes me really uncomfortable. Why would you want to go outside that high in the air?
I think it's pretty cool. I would do it.
I would not. No way. I usually do go in towers. I haven't been in the CN Tower, not for any specific reason. I've been in the Calgary Tower several times. I've been in other towers. You know, someone always makes me stand on the glass floor, which I'm not really into. But I do like going up in the towers and seeing the views and everything. But I haven't been in the CN Tower. Maybe the next time I go, I will. So the 15-meter deep foundation took about 4 months to dig and build back to grade, which is actually not that long. That's a pretty quick build. Normally, when we do these large condo or office towers, it takes probably 4 months just to dig to the bottom of the hole, and then another 4 months to get out of it. It takes a long time to get out of the ground.
I would think the CN Tower probably has a much smaller footprint or below ground, I guess, volume than typical residential towers would have, would it not?
That's true. It doesn't have underground parking. They used a hydraulically raised slip-form style concrete formwork that moved about 6 meters per day as the concrete set below. So essentially that means, formwork is the structure or the mold that they build and they pour the concrete into to form the different walls and slabs and columns of a building. And so they used a type of formwork that they could basically raise up as they were pouring. Typically, this type of formwork is used in continuous pours. They didn't do continuous pours here. They ran pours Monday to Friday with a small crew. But the slit form would raise up about 6 meters per day. So it allowed them to kind of just slide that formwork up as they continued to pour the concrete and build the tower. And this slit form style pour was a pretty new tech at the time. So, that was really interesting that they chose to use that instead. That type of form really only works when you have the same size structure as you go up. It doesn't work when you've got, columns and floor plans and walls that you have to change your formwork then. And they usually have what we call tables. And so, they put the tables under the floor and they pour the concrete on top. And then after that sets enough that they can move the tables, they take the tables off and they bring them up above and they put the next floor up.
Yeah, it's really cool, all the high-rise construction and how all of these different engineering tools and concepts, they all fit together to eventually make a really tall tower in this case, or a tall office building or residential tower. It's really neat how large buildings are constructed.
Yeah. And so, for most of the towers in Calgary, they're done with concrete construction, concrete structure. But some of the towers, for the larger towers, they usually have the core and the columns will be concrete, but then they'll use what's called Q-deck, and it's looks like a corrugated metal sheet that makes the bottom of the floor. So instead of using the tables, they'll use Q-deck that'll stay in place permanently, and they'll pour the concrete on top of that. I think it's just a bit of it adds some strength to the concrete, so the floor slabs don't need to be as thick when you've got a really, really tall tower. At least that's my understanding. Again, not a structural engineer, so I am making some assumptions, but I have seen on some of the larger towers they use Q-deck. For most of the towers that I've worked on, we use concrete. The nature of the tower design for the CN Tower meant that they had to sleeve the concrete. They ran steel cables, tendons through these sleeved ducts, and then post-tensioned the cables once the concrete was poured. Unfortunately, there weren't sufficient supports for the ducts in some locations, resulting in the displacement of said ducts and impairing their ability to run those cable tendons through the ducts, and also impaired their post-tension exercise. Some of the ducts were blocked or resulted in kinked cable paths. So there's a really interesting diagram that I found in one of the reports that showed all the locations of all of the tendons, and then it showed which tendons were damaged and not used, which ones had blocked or which ones had broken or lost strands, and which some were excess, etc. And so we've put that up on the website for you to take a look at if you want. I thought that was really interesting. Based on that diagram, there was only one tendon that was completely blocked and not used, but there were several that had broken or lost strands. So there was still some functionality to it, but it wasn't, full strength. They use kind of a pie chart to tell you how many of the strands or what percentage of the strands were broken or lost. So really interesting diagram. Please go check it out. Failureology.ca. The stress on both ends of one of the cables was so great that it resulted in a loss due to grip failure on the far anchor head. And that stress, was so high that it lifted the stressing jack off its seat. Because the construction proceeded through winter, the concrete and post-tensioning of the steel cable tendons had to be able to withstand severe weather conditions, such as high winds and cold weather. So they basically built this tower through, I think they ended up building through 2 winter cycles. And so they had, all of their construction methods had to be able to withstand the cold winter, the high winds, as well as the summer heat. So they had to be pretty creative with their means and methods to building this tower.
Yeah, that's a lot of things to take into consideration during the design phase of the building of this, and also during the building process. A lot of things, and temperature fluctuations and high winds to take into consideration to make sure that your tower doesn't collapse.
They also had to grout the tendons in the winter. The grout protects the tendons from corrosion, but since they couldn't grout them in the winter, they had to accommodate for corrosion, and that made it hard to maintain uniform final stresses across the tower. This is really cool, and as an HVAC designer, I really liked this part. To protect the steel cable tendons against corrosion until they could be grouted in warmer weather, they blew about 190 liters per second of oil-free air at ambient temperature into each of the tendon ducts to achieve 3 air changes per hour. So they essentially blew these duct shafts ran from the bottom of the tower to the top, and the cables ran in the middle of them. And so they brought clean, dry air that's heated to room temperature through those duct shafts continuously to the point of 3 air changes per hour. And that's how they protected any moisture from building up on these cable tendons and from corroding the cables.
That's really, really cool. I did not know that.
I know. These, again, yeah, I thought this was just a tower, but it's so much more interesting. Also related to the grout, the water to cement ratio had to be just right. So they started off with a thicker grout, but it was really, really hard to pump. They have to pump this grout to the top of the tower, and it was just too thick. The pressure that they needed to get it up that high, it just wasn't working. And it also set very, very quickly. So they would mix it and it would set almost immediately. They eventually found a mixture that I believe was 1 part water to 2 parts cement that eventually did work. And so they were able to grout the tendons into their anchors. They also mixed the concrete on site to maintain batch consistency. That's not something you see very often. Although I will say quality control measures for concrete production have definitely improved over time. You can, for the most part, submit your order on your mix, what you want in it, the strength, etc. And there are limitations to what they can produce, but your mix can be catered to your design requirements. And maybe that wasn't the case in the 70s, or maybe they just chose to mix it on site just to make sure they had a consistent concrete mix. That does sound very labor intensive, though.
I have worked on a couple projects that have had a batch concrete plant on site. We were really, really far away from anywhere that could deliver cement in a reasonable time period. So the solution was to actually have a batch plant on site where we could make cement basically on an as needed basis. It was a really neat project to be a part of. But like Nicole said, that's very, very uncommon in construction.
Well, and also, and I know this is wrong, but I'm picturing some guy mixing cement in a wheelbarrow because that's the only way that I've ever made cement. I know they didn't do that. That's ridiculous. But that's what I'm picturing. And I'm like, that seems silly. I realize that's me. But that's what I picture when I think of, mixing the concrete on site. And another thing that again, interesting, very interesting. They used massive plumb bobs hanging from the slit form, and they viewed those from small telescopes on the ground. They used those to make sure that the tower stayed vertically accurate, so to make sure that they built it plumb and, to true vertical. The tower varies from true vertical accuracy by only 29 millimeters throughout the entire tower. That is extremely impressive accuracy. I don't know what the tolerances are for today's construction, but I have to assume they're more than that because 29 millimeters is not very much.
Yeah, it's like the width of your thumb if you have fat thumbs. It's like slightly more than an inch. Like that's a very tight vertical tolerance, and great for them for achieving that good vertical tolerance back in the 1970s.
And across 500 meters. This isn't a 2-story building. This is equivalent to 147 stories.
That's a really long way away from the ground.
Yes. I know, my hands are sweaty again.
I think one of the tallest buildings we have here in Calgary, I believe it's 50 stories or right around 50 stories. So this is kind of 3 times the height of really anything that we have in Calgary. At least I'm going to say 2 to 2.5 times the height, in case there's a taller building I'm not sure of. In August of 1974, they raised 12 giant steel and wooden bracket forms with cables and jacks to the top of the tower, which they would use to form the pod at the top, which houses all of the observation decks and the restaurant and the skywalk that you can do, or the edgewalk you can do around the outside of it. The pod is supported by a ring beam that forms a 12-sided polygon, or a dodecadon, if you're into the names of polygons that have multiple sides. The tendon units in the ring beam were one of the more delicate design problems, as they had to arrange all of the stress patterns symmetrically, and all of the anchors had to be located towards the inside of the beam. Each tendon was placed in the identical position, reaching 180 degrees around the ring beam and offset 30 degrees from the adjacent tendons. All 24 anchors were stressed sequentially to ensure the closest approximation of symmetry at all times. So it's like tightening the lugs on your car tires, except there's 24 of them, and it's a giant building.
I also found this 12-sided polygon tendon design really fascinating, and I found a really good diagram of all of the different tendons and where their anchors are located and how those all worked within the ring beam. That is also on the website, so go check that out, failureology.ca. On the page for this episode, there'll be a few pictures, and the 12-sided polygon will be one of them, as well as the diagram of the different tendons throughout the tower.
Picture's worth 1,000 words.
Yes.
And unfortunately, this is a audio medium, so we can't convey a picture to you.
Which is why we have a website.
So they had a crane on site, which is really handy to get materials up to the top of where you're working. But the U.S. Army sold one of their Sikorsky S-64 Sky Crane helicopters to civilian operators. And this is a helicopter where the cabin portion of the helicopter is right at the front, and then there's a whole bunch of space at the back where they can haul very large tanks, and they can haul very large pieces of material that need to be flown up. So this is really cool that they used this Sky Crane helicopter, and we'll put a picture of that up on the website as well. They were able to use this helicopter to move materials from ground level all the way up to the top of the building. It's, at least in my experience, it's not very common that helicopters are involved in building construction. So they used the helicopter to remove the crane that was already there, and then the helicopter flew the antenna up in 36 different sections, and they even named the helicopter. The helicopter was named Olga.
Sure was. That's a great name for a helicopter.
By using Olga the helicopter, construction on the antenna section, the installation of it, was reduced from 6 months initially to 3.5 weeks, so significant time savings. Plus, you got a helicopter to build your building, which is really cool. On April 2nd, 1975, after 26 months of construction, the tower structure was finally complete. As a side note, there's apparently only one person who died during construction, which, if you listen to some of our previous episodes, specifically the Panama Canal episode, that's a significant improvement over some earlier construction projects. Jack Ashton was a consultant for the concrete inspection company. He was hit on the head by a falling piece of plywood and unfortunately died on impact. The average hourly wage at the time was $8 an hour, which is equivalent to $42 an hour today. There was also danger pay, which equated to $1 an hour for every 100 meters over 300 meters. That doesn't actually seem like that good of danger pay.
Well, if $8 equates to $42, then you're getting a little over $5 an hour extra per 100 meters.
But only over 300 meters, so you'd only make an extra $2 per hour, really.
But now that's worth $10 an hour. So if you were working at the top, you'd get $52 an hour today.
I guess it's better than nothing, right?
Yeah, I mean, well, I think the chance of surviving a fall over 4 stories is not great. And so once you're up that high, doesn't matter. I don't know. I don't want to go up there. My hands are getting sweaty again. So let's stop talking about this part. 2 years into tower construction, plans for the Metro Center were scrapped, which meant that the CN Tower ended up being pretty isolated on railway lands, which was a light industrial site at the time. And this made it pretty challenging for tourists to access the tower. That was then. Now the tower is surrounded by lots of things, including the Rogers Center where the Blue Jays play and the Scotiabank Arena where the Maple Leafs lose all of their hockey games. The tower also has a restaurant called 360 Restaurant, which completes one revolution every 72 minutes.
They've made changes and completed renovations on the tower over the years. In 2008, they added glass panels to one of the elevators, reaching a world record for the highest glass floor paneled elevator in the world at 346 meters. In 2011, the Edgewalk attraction opened, allowing people to go outside and walk around the roof of the main pod.
I don't know why you'd want to do that. Not appealing to me.
I mean, you could pay money and be really scared.
You couldn't pay me money to do that. Not interested.
I will take your spot then to go on the Edgewalk.
Yeah, you can have it.
Excellent.
I'll wave to you from below.
Okay, that sounds good. There are 1,776 steps to the main deck and 2,579 steps to the skypod. So if you're there and you get the opportunity, you can count and verify that those are the correct numbers.
We want a full report.
In triplicate, so you got to walk up and down a few times. So CN Tower holds a charity stair climb event twice a year, and it takes the average climber 30 minutes to get to the main deck, but the record is 7 minutes and 52 seconds. Good on that guy. I don't think I could go faster than that.
So, Brian, I believe you've done the Calgary Tower stair climb.
I have done the Calgary Tower stair climb a number of times when I was much younger and much fitter and much better looking. I don't even know if I made it up the Calgary Tower in 7 minutes and 52 seconds, and I felt I was going pretty quick.
How many stairs? Do you know how many steps that is? Like just approximately?
The Calgary Tower has 802 steps in it, so it's slightly more than half the number of steps to get to the main deck. And I think it took me more than 7 minutes and 52 seconds to make it up the 802 stairs.
I mean, to be fair, that's 7 minutes and 52 seconds. That's a world record holder. That's probably someone who's a professional athlete or someone who's trained extensively for that record.
That's a lot of time on a stair climber.
You don't just set that just for fun on a Sunday. You train for that.
On April 16th, 2018, which was actually a few days before I was at Rogers Center to watch the Blue Jays play, there was some falling ice that fell off the CN Tower, and it punctured the roof of the Rogers Center.
For those who don't know, Brian loves bat ball almost as much as he loves airplanes.
And dogs. Those are the top three things that I like.
Yeah, I'm on board with the dog one. Definitely. All in all, this tower is actually really interesting. I thought it was just going to be a concrete tower, and whoop-de-doo, it's a tower. But all of the different techniques that they used were interesting. They used some really old tech, some new tech. They had some problems to overcome. This is a little bit off-brand for the show, but nothing went catastrophically wrong. The construction went fairly smooth. All in all, this was much more interesting than I was expecting, and I'm much more interested in going up the tower next time I'm in Toronto, now that I know all of these things. And I already feel bad for whoever is with me that has to listen to me tell them all of these things. Maybe I'll just put the episode on and let them listen to it. I should probably do that as a preemptive exercise, mandatory listening before going up in the CN Tower with me.
That's a good solution. Or you can just give them the episode as you go up all of the stairs, and then they don't have to hear you complaining about things.
That's true. Distract me. Then I won't complain. It's a good idea.
I mean, that is a lot of steps to go up.
I'm taking the elevator. Not the glass floor one, though. I'll take the one. The glass walls are fine because I don't think I have a choice, but I'm not taking the glass floor one. You probably have to pay extra for that one anyways.
Maybe you have to pay extra not to take it.
Fine. Sold. Where do I sign?
So there you have it. The CN Tower in Toronto, Ontario, Canada. One of the American Society of Civil Engineers' 7 wonders of the modern world. All things considered, and compared to many of the other things that we've covered on this show, the tower construction, like Nicole said, went pretty well, and it's a pretty cool endeavor. Not everything went to plan, of course, but they got to work with some new tech and some old tech to make what is still the tallest freestanding structure in the Western Hemisphere.
For photos, sources, and an episode summary from this week's episode, head to failureology.ca. If you're enjoying what you're hearing, please rate, review, and subscribe to Failureology so more people can find us. If you want to chat with us, our Twitter handle is @Failureology. You can email us at thefailureologypodcast@gmail.com. You can connect with us on LinkedIn, or you can join our Patreon page, check out some really interesting mini failure episodes, and support our show. There are links to all of these in the show notes. Thanks everyone for listening, and tune into the next episode where we'll talk about 3 Mile Island, a partial meltdown of a nuclear reactor in Pennsylvania. Bye everyone. Talk soon.